Hi, I'm Xiaomar from the National University of Singapore. I would like to present our work, Spatial-Temporal Graph Transformer Networks for Pedestrian Structure Prediction. Crowd modeling is an important problem to both computer vision community and robotics community. It has many important applications, for example, urban navigation and self-driving cars, and also building realistic game simulators, and also the building robust surveillance systems. However, the performance of the crowd modeling methods are still limited because the real-world scenario is far more complicated than we imagined. In this example, we have a very complicated scenario, a crowded market with complex crowd interactions. For example, the strangers tend to avoid each other when passing by. However, friends or families will try to stay in group, and this will sometimes form a static group in the crowd system, and sometimes this will cause trouble to a lot of the crowd modeling methods. The most difficult part of here is that we have to guess the intention of the pedestrians. For example, in this case, the man in the back is actually tries to move forward. His intention is to move forward, although there are a lot of free space around him, so he will not choose to go there. So there are many types of the different complex interactions and attentions in the crowd system, and it's pretty hard to model this in this case. So we observe that when people are moving in the crowd, there are actually different levels of the attentions. First, people have complex spatial interactions. For example, as we just mentioned, fellows walk together while strangers tend to avoid colliding with the others. Next, one decides his future actions considering how his neighbors would react to his actions, which means that he pays attention to the past and the future trajectories when choosing the action for both his own trajectory and also his neighbor's trajectory to understand their intentions. So in this work, we built such a complex system as a spatial temporal graph, and we address the issue by only attention mechanisms. Prior deep learning-based approaches use the RNNs to model the temporal dynamics, followed by a spatial module to model the social interactions. So here, the spatial module is normally a simple social pooling layer or a simple graph neural networks, and RNNs is sometimes just the LSTM or the GRU. However, there are two major issues of this framework. So first is that the modeling of the long-term temporal dependencies is hard for the RNNs. And this has been proven in different literatures, including specifically the natural language processing field. So the modeling of the long sequences is difficult for the RNNs. And the second is the most of these approaches use relatively simple social modeling modules, for example, like the graph pooling or some relatively simple graph convolutional methods, for example, GCNs, which can only capture simple spatial attentions. So in this work, instead of the RNNs, we consider transformers from a different perspective. So transformers has been widely used in the natural language processing, and it has replaced all the RNN models. It has achieved great success in various tasks, including machine translation, text generation, and machine comprehension, etc. So we wanted to think about, can we use transformers to model the complex attentions in the crowd system? So the answer is definitely yes. But however, there is one problem, is that the transformers can only be applied to unstructured data sequences, and applying to the graph sequences is pretty difficult. In this work, we introduced the STAR framework, which stands for the Spatial Temporal Graph Transformers. So the STAR separates the spatial modeling and temporal modeling into two different modules. For spatial modeling, we treat each pedestrian separately, and we use a standard transformer to capture the temporal dependencies between them. So this is better compared to the RNNs because the temporal modeling ability of the transformers is significantly better than the RNNs. We also introduced a novel spatial transformer that can be applied to general graph structure data, so which improves the spatial modeling ability compared to the standard graph convolutional methods, because in the standard methods, for example, GCN, it doesn't consider the attentions between the different pedestrians, and different pedestrians will pay different attentions to the neighbors. For example, a passenger, he will consider all the others are equally important, while if you are in a group, you pay less attention to your fellows. And the spatial transformer and temporal transformer, they interact with each other to capture the spatial-temporal interaction of the crowd. Specifically, we implement the spatial transformer with a TGConv, with a transformer-based graph convolution methods introduced in this paper. So the intuition behind is that we can actually treat the original transformer as a message passing process on complete graph. So imagine that in this simple example, we have 3 nodes in a graph, and if we connect every single node with all the other nodes and add a self loop to each node, this becomes a complete graph. And the transformers, they basically just do the self-attention, and self-attention is exactly on a complete graph. So we can treat the transformers as a message passing process on a complete graph. And so the message pass, if we have the idea of the message passing, we can easily generalize it to an arbitrary graph. So on an arbitrary graph, we just denote the message from each node to the other node using the self-attention mechanism, and we can implement the transformers on an arbitrary graph, and we call this a TGConv, transform-based graph convolution. We use the TGConv to develop the spatial transformer module. So this is the overall framework of the star. It consists of 2 encoders and a graph memory to smooth the predictions. In the encoder one, we separately use a spatial transformer and temporal transformer to process the initial trajectories, and in the encoder to interleave between the spatial transformer and temporal transformer to capture deeper interactions. And an additional graph memory is used to smooth the predictions of the temporal transformer, because for the time series data, the ability of the transformer is not as good as the RNNs. So we have to use a graph memory for the smoothing. The prediction result is added back to the history and predict the next step. So this is the overall experiment results. We performed extensive experiments on 5 commonly used trajectory prediction datasets, the ETH, Hotel 01, 02, and UNIV. So there are 2 different versions of star. The first is a deterministic version of star. So the deterministic star has outperformed the state-of-the-art deterministic trajectory predictor SRLSTM on overall performance. And the stochastic star, every time we insert a random number to the star framework, such that we sample 20 times, and we choose the best performed action compare it with the other baselines. So the stochastic star has significantly outperformed all the other baselines by a large margin. So we also did some visualization to better understand the prediction result. So as you can see that the first row is the prediction line of the state-of-the-art method SRLSTM. We can see that SRLSTM has actually trajectories that seems to overfit onto the spatial interaction, while the star is better in terms of this and predict better trajectories. We also visualized attention values learned by the last spatial transformer. So you can see that actually our attention mechanism successfully learned a reasonable attention function, which is close to the real crowd behaviors. Our code is available here, so if you're interested, please scan the code and play with it, and come to our Zoom session to discuss with us. Thank you so much for your attention.